Dear friends, today we will learn bus voltage control. Consider any bus of the power system. Say this is ith bus. The bus voltage is represented by Vi and delta I for the ith bus, and the remaining part of the power system is not shown. Remaining part of the power system so focus on ith bus only. The power injected into the system is represented by Pi plus J Qi. Let us denote the load connected at ith bus as PLI plus J QLI. The generated power injected, let us denote this by PGI plus J QGI. Earlier we have used the same notation, right? For any bus, ith bus, PGI plus J QGI is net generated power injected into the bus. This is the net load. So difference of the corresponding active and reactive powers will be Pi plus J Qi. It means we may write Pi is nothing but equal to difference of these two real parts, PGI minus PLI. What about QGI? QI will be equal to this QI will be equal to QGI minus this QLI. Is not it? So from where this power is coming? Generator connected at ith bus. So denote this generator also. So denote this reactance also. Let this is EGI angle delta GI. The voltage phasor here, you are aware of that. The generated EMF here is represented by EGI with angle delta GI, and at this bus voltage is VI delta I. So let us denote this reactance by XGI for the generator connected at ith bus. So this part is for generator. So how to write these two power? You might have studied in power system 1 this real power, or in transmission line also. If you know the sending end voltage, receiving end voltage and reactance, so you may write power, you know, right? So just write it PGI, this PGI will be equal to magnitude of this represented by EGI, magnitude of this VI upon this reactance XGI sine, this is delta GI and this is delta I. So this will be, resultant will be delta GI minus delta I, is not it? Sine of delta GI minus delta I. Remember, for transmission line, sending end voltage, receiving end voltage upon reactance, sine of delta, where delta is the phase difference of the two voltages at sending end and receiving end. If you are taking reference as 0, then that will be exactly delta, is not it? So, but we have represented this as delta GI. This is delta I. So difference will be delta GI minus this sine of this. This is active power, right? Let us say this is equation 1. Similarly, write for this QGI. So I am writing here QGI will be equal to this QGI. Similar to that PGI, right? QGI. Remember, during load flow solution, we have studied that active power P is more dependent on delta or V? And what about Q? V, right? Okay, we will discuss that. Just remember as of now, and then discuss, right? So first, help me in writing QGI. So QGI will be, first take the difference of these two. So EGI minus VI upon this. How to write the current? You know, EGI this minus VI upon, I am writing here upon XGI times this VI. You might have derived the same relations for PI and QI. Active power flow, reactive power flow, right? Write it equation 2. So we are going to control bus voltage of any bus of the power system. So consider any bus, bus number I, ith bus. So for ith bus, we have used the same notation as we started our load flow solution. So you know, you are aware of these symbols PGI, QGI, PLI, QLI, right? So net power injection into the system at this bus will be PI plus JQL. We have discussed it, right? These are the loads, active load and reactive load. So in case of increased Q, you need to supply more Q, is not it? In case of not only this Q, your bus is connected to the power system. So in general, we can say that using load flow solution, whatever the values of the four variables, Pi, Qi and delta I and PQ, delta and Vi, is not it? Corresponding to ith bus, the four types of variable will be these four variables, Pi, Qi, Vi, delta I. So for the values of these variables obtained after load flow of the power system, if this demand is more than what you are having, what we will do? If this demand is more, then it means you need to adjust delta, because this is more dependent on delta. Not only dependent on delta, we have seen in Newton-Raphson also and fast recovery like that. So mainly we need to focus on delta. And how to adjust delta? Okay, focus on this. Okay, we will come to that portion later. Again, discuss for this QI. If QI demand is more than what you are having, in order to maintain the exact QI demand obtained from load flow, what you will do? You know that QI is nothing but the difference of these two, as Pi is difference of these two. So suppose this demand has increased. What is solution? You will do load shedding. That is not the solution. You have to fulfill this. So you have to adjust this. In order to get this, finally you need to adjust this. How to adjust this? What is PGI? PGI is the active power supplied by the generator. So how to adjust PGI? So your governor setting will be adjusted. How much you should adjust your governor setting? Governor is basically supplying the power through the governor. So governor setting should be such that the net input to the generator provided by turbine must be equal to that required PGI here plus losses occurring here. Is not it? and vice versa. So finally you will adjust the governor setting for this PLI or PI to maintain this PI required after load flow. Similarly, focus on QGI. So this is the value obtained after load flow. This is QI at ith bus. So focus on this equation. QI is nothing but difference of these two. This is the load reactive power demand at ith bus. So don't do any shading. Provide proper solution. So that can be provided by this. You will adjust this, and QGI is nothing but this. So finally you will adjust this. What is this? EGI. So how to adjust this? With the help of generator excitation. You will change excitation in your synchronous machine also. You might have studied with the variation of excitation. What is the effect of EGI on EGI? Is not it? So two-way. Finally what we are going? We are going to control voltages. So voltages of buses. It is having two parts, magnitude and angle. So this angle is related with active power. As we have discussed, P is more dependent on delta, and this is related with reactive power. If voltage of any bus is lesser than the desired, it means the net reactive demand is not being met, and vice versa. Is it clear to you? So how to control the voltage of any bus? So you can answer, okay, these are the values obtained from power flow, load flow solution. So in order to maintain this, it means in order to maintain this, we have to adjust this. This can be adjusted with the help of governor setting. Governor setting will be adjusted so that the turbine output given to the generator input must be equal to this PGI plus losses. Similarly, to achieve this QI demand, you need to adjust this quantity, load quantity, don't disturb load customers, right? So you need to adjust this, and QGI is written given by this. So you need to adjust this. So in order to adjust this, you need to adjust the excitation of the alternator. That is a simple answer. So bus voltages can be controlled in various ways. We have discussed using generator settings and governor setting. Other ways also that you can use regulating transformers also. You know that transformers can boost voltages. It can step up or step down. Is not it? So using transformer also, we can control the bus voltages of the power system. So bus voltage magnitude or angle both can be can be controlled with the transformers. You know that bus voltage magnitude can be done, right? What about phase angles? Can we do that? Both can be done. We will see one by one. How? Okay, one more thing. If you have changed its excitation and it has reached its maximum capacity, if still more Q demand is there, then what will do? It can't supply more than its capacity. So in that case, you need to control voltages with the help of some other VAR sources. That may be capacitor, synchronous condenser, etc., etc. Right? So this can be controlled beyond the can't be controlled beyond the capacity. Within the capacity, we talk within the capacity. If still the demand is more, then you need to add capacitor, banks, condenser, etc., etc. Right? Okay, so next we will see how to control bus voltages with the help of transformers. So let us see. This is transmission line. I will rub this. So let us see the three phases of line are represented by, this is A phase, RYB or ABC, represent the phase voltage VAN. This is VBN, phase voltages between phase and neutral, and this is VCN. You want to boost, you want to increase the voltage magnitude. First draw this diagram, and let us represent these terminals with corresponding A dash, B dash and C dash, so that the phase voltages will be represented by VAN dash, this phasor VBN dash, and this phasor VCN dash. Let us ground it. This is neutral, grounded, right here N, and this is A. So connect with this line, connect with this A. Let us represent this A to avoid confusion. Let us represent this as B and this as C. So connect this with B. So B is here. Connect this with B. This is C. So connect this with C. Diode. This is neutral. These are star connected windings. Back here N, star connected. And this is A, so connect this with A. This is A. This is B. So where is B? Here we have B. Okay, right here, B here, and take this as B. First draw it, then we will discuss. This is C, so connect this with C. So let us say this tap changing setting T. This T can be varied from here till here. We can vary tappings. So corresponding voltages, this is AN, A phase, so T times VAN we will get here, corresponding to this T ratio. If T is more voltage we can get. If T is 0, we will not get any additional voltage in this phase. So suppose we are getting for certain setting T, we are getting corresponding of the same phase voltage T times VAN of the same phase. Suppose tapping is 10%, so we'll get 10% drop of whatever we are getting this phase voltage. Is not it? So basically we are boosting this level by 10% or T% we can say it. Is not it? Similarly for B phase we will have T times VBN. For C phase we will have, because everywhere we have same setting in the three phases. Is not it? So this way what we are doing, we are increasing the voltage magnitude, but we are not disturbing the phase angle. Is not it? Just we are adding the corresponding voltages of the same phase. So phase difference angles will be same, only magnitude will be increased. So we are increasing the magnitude, voltage magnitude only. It means we are going to control the reactive power flow of the line. reactive power demand can be met by this method using regulating transformer. Is it clear to you? So what about other one? What is other one? Active power. Active power flow. So that can be controlled with the help of changing the phase angle, not voltage magnitude. Phase angle, is not it? Okay. So I will draw another. Okay, let us draw here. So this is delta connected. Just draw it. Let us denote it again by ABC. Okay, first draw this also. Let us draw this also. So mark it as A, B, and C. So let us connect this with A phase. This is A, the same of the line, and draw here B somewhere. So this is B. So B will be connected with this. And if this is C, so mark here C, and this will be connected with this. So this is C. So you know that here the phase voltage will be VAN. Here the phase voltage will be VBN. Here it will be VCN. So for this case, here the phase voltage is VAN. Here the phase voltage is VAN dash. So that is different from this, as we have added some extra drop here. So we may write this VAN dash equal to VAN potential here plus rise in potential will be potential here. This is the drop between this point and neutral. VAN is drop between this point and neutral. So neutral is common. So basically potential here will be potential at this point plus rise in the potential, is not it? So we may write this plus this is T times VAN, is not it? So we may write 1 plus T VAN. This T is a scalar. So it is affecting only magnitude of this, is not it? 10%, 20%, 5%, whatever it is, just it will affect the magnitude of this without affecting the phase angle. That was our target for this, is not it? So or you can write it alpha times VAN. So alpha, you will calculate what should be alpha in order to change this magnitude by this 1 plus the alpha. Similarly, for this, okay, I am writing this A here. So take this. Similarly, for this side we are taking first one. So take this one. And left side, so take this one. Just draw it. So these are the corresponding points A dash, B dash, and C dash. Any confusions you can ask. So again the settings must be same. If this is T again, so this must be T, this must be T, is not it? So whatever voltages has been added in the corresponding phases. The resultant again we can obtain here. So again say this is VAN dash. This is VBN dash. And this is VCN dash. This time we are adding some extra drop in phase A. Whatever potential here, it is here, right? We are adding this, but this drop is not in phase with this. This is parallel to this. So this is in phase with this. This one is in phase with this, and this one is in phase with this. Is not it? Okay, we can draw a phasor diagram for this. I am writing this. Okay, so first draw the phasors corresponding to three phases. Say this is phase A, this is phase B, this is phase C. This is neutral, this is neutral. Phasor diagram, you are aware of that, right? Rotating vectors. So relative positions of this will be these are corresponding to RMS values, is not it? So for three-phase balance system, the RMS value of all the three phases must be same, and the phase differences between two consecutive phases will be 120 degree, is not it? So let us represent it with phasor A, B, and C. So this will be line voltage, is not it? VBC. VBC is nothing but VBN minus VCN, is not it? If you will write minus, so it will go there. Resultant of these two, it will be there, right? Is not it? Parallel to this. But this is line, right? And you are adding one extra drop in phase A, that is in phase with, we will check whether phase and out of phase, but parallel to this, because we are having two half here, right? So in phasor diagram we are already having VAN, and we are adding some T times VBC, is not it? So that phasor will be in parallel with this, and we will write this phasor by T times VBC, is not it? This is VBC. So parallel, is not it? So resultant will be this. Resultant means this will be VAN dash. If this phasor is VAN phasor, this is VAN phasor, this is VBN phasor corresponding to this V, this is VCN phasor. So this VAN dash can be represented by this phasor diagram. Any question here? Are you getting confused if you have written V here or here? Doesn't matter. You can change the phase sequence just by interchanging any two terminals. Is not it? So this VAN dash in this case, this was for previous case. So for this case, we may write VAN dash will be equal to this VAN phasor plus T VBC. What is magnitude of VBC? Root 3 times that of this. Magnitude of this RMS value will be root 3 times that of phase. You know that. Okay. So this phasor, taking this as reference, you have to write this phasor clockwise, but 90 degree apart. So you will multiply with J or minus J? Minus J. You know that, right? Because if you are multiplying with J, then this will be this phasor, right? So you will multiply with minus J, and magnitude of this will be equal to root 3 times that of. So can we write this as, okay, write VAN plus, at place of T, write T, and here you will write in place of VBC minus J root 3 VAN phasor. With respect to this phasor, you know how to multiply two phasors in polar form. So one phasor as it is with its original magnitude and phase angle multiplied with the next phasor, is not it? So next phasor is having magnitude root 3 times of this and magnitude this T is there, is not it? So finally you will get 1 minus J root 3 T times VAN. Are you getting this or not? So for a smaller value of T is generally a small, you are going to boost up 5%, 10%, whatever, that is a small, isn't it? So if you are going to take magnitude of this phasor, that will be nothing but magnitude of this times magnitude of this. Magnitude of this will be under root this square plus root 3 T square. So T is small, so T square will be again very small. So that can be neglected, or you can say that it is hardly affecting the magnitude of this phasor, but it is affecting the phase angle of this phasor. Is not it? And you know that our target was to control the phase angle rather than magnitude of the bus voltage. Clear? So this way we can control the phase angle of the voltages. Or in other words, phase angle means active power flow of the transmission line. Is it clear to you? Okay. So if you have used regulating transformer for these purposes, either controlling voltage magnitude or phase angle of the voltages, bus voltages, then your Y bus will be modified now. And again you need to perform load flow analysis. So how to represent that? I will represent it, and then today's class will be over. And it is almost finishing your unit 1. So let us say let us represent any two buses and one line connected in between the buses. So let us say this is ith bus and this is jth bus, and you are connecting these two buses and represent the line admittances or impedances by say Y admittance, right? So you know that the voltage, bus voltage of this is VI delta I, and here this is VJ delta I. Okay, if you are representing the power flow from here into the system SI, and here you are representing SJ. If we are going to use regulating transformer here, suppose here you are going to add regulating transformer. So this time represent this transformer by this and show the tappings here, whatever T or whatever it is. So this is representation of voltage control bus and controlled by regulating transformer. So the potential of this will be different than the potential here, is not it? And the potential here was VI delta I, and you are going to use regulating transformer, means you have controlled VI and delta I both. So both has been changed here at this point. So here you will represent, this also can be written as here alpha or A VAN. So alpha for this case is 1 plus T, alpha for this case is this, right? So directly we may write here alpha VI phasor. I am writing phasor because this is nothing but VI phasor. VI phasor is equal to this VI delta, is not it? So this phasor has been changed now. Clear? Once this phasor has been changed, you need to construct new bus admittance matrix because current will be changed here, is not it? Suppose you are writing this SI, so SI will be nothing but VI II star. II currently is there, right? Corresponding to this SI and VI, you know what is II? Because SI, VI, II star, right? Corresponding to this, now the apparent power will be corresponding to this. So II will be modified now. So for Y bus formation, you have applied KCL corresponding to I phasor, Y phasor and V phasor. Is not it? I phasor is nothing but that matrix is equal to bus admittance matrix times which phasor vector? Voltage. But now that voltage phasor has been modified. It depends on which bus you are going to use, regulating transformer or any other means. Is not it? So now our conclusion is that once you have used regulating transformer, so you need to again calculate the bus admittance matrix as you have modified the bus voltages. Is it clear to you? Thank you for today. Any question?